This brief tutorial will illustrate the two different ways which tendons may be specified. 1. As only a load, and 2. As a load with element properties. Our model will consist of a 2-span beam. We will use the same cross-section for each span, a 10-inch by 20-inch concrete section. The first span will have a tendon model as a load only. The second span will have a tendon model as an element, and both tendons will have an area of 1 square inch. Initially, no losses will be included. We start by going to the Define Section Properties Frame Sections command. Our new section will be concrete and rectangular. For our section, we will use a depth of 20 inches and a width of 10 inches. Next, we will draw the frame objects. We draw both frame objects from the outside in so that the local eye joints will be on the outside. Next, we select the outside joints and assign a roller support. The inside joint gets a pin support. Now we will define a load pattern for the tendon load. It will have a type of pre-stress. And we can delete the dead load pattern as it is not needed. Next, we will define our tendons. We will add 2 new tendons. Our first tendon will be called T-loads, and it will be modeled as a load only. We can specify tendons by diameter or area, and in this case we will use an area of 1 inch square. Although this tendon is not an element, an area is still required for the calculation of loads and losses. Our second tendon will be called T-elements. And it will be modeled as an element. And it will also have an area of 1 inch square. Next, we will draw the tendons. The span on the left will get the loads tendon. And we click on the Add button under Tendon Loads to add the tendon force. We jack from the eye end, and loads can be specified as either a force or stress, and hence why you need an area to be defined. Here we will specify a force of 10 kips. For this particular model, we will set all of the loss parameters equal to 0. For the right span, we will draw the elements tendon. Note that we draw the tendons in the same direction as the frame objects. Again, we specify a tendon force of 10 kips and leave all loss parameters set to 0, although the other loss parameters are actually calculated by the program when using a tendon modeled as an element. Values entered here would be in addition to those calculated by the program for this tendon. We are now ready to run the analysis. We will shut off the modal load case as we are interested in only the tendon case. A right click on the far left joint shows a displacement of 0.00139 inches in the X direction. This is for the frame with a tendon that was modeled as a load only. The joint on the far right moves in the minus X direction 0.00133 inches. Why the difference in deflections when the initial tendon forces were the same? It is because the tendon on the right was modeled as an element and has elastic shortening. Next, we will display axial forces. A right click on the frame object on the left shows that the entire 10 kips of tendon force is being carried as a compression force in the frame object. The force in the tendon object in the right span is only 9.62 kips due to shortening. By statics, the force in the beam should be equal and opposite, and a right click on the frame shows this to be true. The frame has 9.62 kips in compression. We can get the frame on the left to match the frame on the right by applying an elastic shortening stress of 0.38 KSI. We do this by first unlocking the model and then selecting the tendon on the left and deleting it. We will redraw the tendon, again using the tendon that is modeled as loads, and we'll apply the same 10 kip force. All of the friction and anchorage losses will be set to 0, but this time the elastic shortening stress will be set to 0.38 KSI. This is the relaxation from the tendon object divided by the tendon area. All the other losses will be set to 0. We leave the draw mode and rerun the analysis. The axial force on the left is now at 9.62 kips. The same as on the right. Changing to a deformed shape, a right click on the left node shows that the displacement is now 0.00133 inches, which also matches that on the right. In summary, specifying how the tendons are to be modeled, either as loads or as elements, may have a significant effect on the distribution of loads, as well as on the model behavior if the structure is indeterminate. This ends this tutorial on the tendon object.